Welcome back. We're still talking about EM wave propagation, and in this video we're going to consider the power that an EM wave carries as it propagates. Power is important because whenever you want to do something useful in physics and in engineering, you need power to interact with the world. And for electromagnetics, power actually allows us to communicate wirelessly, send a signal and receive the signal. So let us have a look at power. Now, let's start with Maxwell's equation, Ampere's law, in point form. Okay, so recall, I can write this. Sigma E is the current density J, and then Maxwell's correction, like that. Okay, now what I'm going to do here to this equation is I'm going to multiply, meaning I'm going to do the dot product with the electric field on both sides, because I know that power, you have to have some voltage, you have to have some current. I know that from circuit analysis. So on the left I have current, basically I have a magnetic field, so I'm going to get an electric field on that side as well. So now I'm going to do the dot product with the electric field like this, and I suspect that I've got some sort of power. I botched that. That should be a cross. I suspect that I have some sort of power that I'm dealing with once I dot everything together. Now, E dot E is of course the magnitude of E squared on that side, and then I've got plus E dot epsilon delta E delta T, like this. Now, there's a vector identity that you don't need to have memorized. It's that the divergence of A cross B is equal to B dotted with the curl of A minus A dotted with the curl of B. So if you don't remember that, we talked about that very early. That's okay. So we're just going to apply that here with A being the magnetic field and B being the electric field. No big deal. So now this thing that I've written here, this becomes, after the vector identity, H dotted with the curl of E plus the divergence of H cross E equals, then we've got sigma squared, sigma not sigma squared, sigma E squared plus E dotted with epsilon times the time derivative of the electric field, like this. Now, this thing here, so there's a little bit of tricky math going on here. I'm going to try my best to identify these things for you. This thing here, we can look at this as the reverse of the chain rule. So let me just kind of emphasize that in blue. So let's say I had some magnitude of vector field E squared like that, and I took the time derivative of that. So what you would do is, if you were going to take the time derivative of E squared, the 2 would come down in front, cancel with this 1/2, and then you would have E, right? And then you would have also then the derivative of E versus T, which is the inside. So that is the chain rule. So usually you go from blue to black when you apply the chain rule. Here we're going in reverse. So I'm moving the E inside the derivative. So that's the reverse of the chain rule. So if that's not a big deal if you didn't follow that, but for those of you who are up to speed in math, you might find that a little bit interesting. I know I do. Now let's look at a second Maxwell equation. The curl of E, again this is in point form, is negative mu times the time derivative of H. Okay, and again I'm going to bring in now the magnetic field to both sides. So I would have something like this. Okay, and for the same reason that we said about the chain rule, this is actually mu over 2 times the second derivative, or excuse me, the derivative of h squared versus t. Okay, so now we can combine these equations together. So the equation 1 with equation 2, and what we see now, I've got negative mu over 2 times the derivative of h squared, right? Because that is h dotted with the curl of e, so that's directly substituting there. Then I'm going to change this to a minus, and I'm going to switch the order for a reason you'll see in a little bit. So I can switch the order. That's how the cross product works. I can switch the order, but then I need a minus sign. And so this now is equal to sigma e squared plus 1/2 epsilon times the derivative of e squared, like that. Okay, now I can rearrange, and I'm going to integrate over a volume. So we're just some slick mathematics here, like I said. We're continuing with that idea. So I've got the divergence of E cross H. That E cross H seems to be coming up a little bit. Integrate over volume equals, I'm rearranging. This is the time derivative over a volume, 1/2 E epsilon E squared plus 1/2 mu H squared dV, and then minus integral of sigma E squared dV, right? So again, just rearranging that a little bit and then integrating everything over volume. Now, keeping with the slick mathematics, I can apply the divergence theorem to this term here. And the divergence theorem relates a volume to a closed surface integral. So let me do that. So I've got a closed surface now defined by the volume of E cross H, there it is again, dotted with ds is equal to, and then everything else stays the same. So I've got the time derivative of the integral over v, 1/2, v is just some volume. It's just some volume in space. I'm going to be interested later in saying how much power is contained in this volume or traveling through the volume. Okay, so now I've got this equation. And you can interpret this equation as follows. So the term on the left is the total power leaving the volume. I'm going to argue that that's the total power leaving the volume. Okay, and I'm going to argue that this term here is the rate of decrease in energy stored in the electromagnetic field. So this is the rate of decrease, because the negative sign, and it's a rate because of the time derivative, rate of decrease in energy stored in that volume, right, via the electromagnetic field. And then this term here, we recognize this from our calculation of resistance and Ohm's law in point form. This is the ohmic power that's dissipated in the volume. That is dissipated. Nice. Now, the argument goes like this. E cross H, we see E cross H quite a bit in our calculations. We wonder what units does E cross H have? And E, of course, is volts per meter, and if I multiply that by the units of H, which is amps per meter, we see volts times amps. Hey, we know from circuit analysis, that's a watt. So we have watts per square meter. So when we integrate watts per square meter over a surface, watts power per surface area over the surface area, then we just have watts. So this is the total power then leaving V. Okay, so we indeed have a power calculation, which we suspected when we took E times H up there. Okay, now this E cross H turns out to be pretty important, and we give it a symbol in our class, and it's kind of this weird script P, and it's a vector, of course, right? E cross H. And it's got a really cool name to it. I have to be honest, I love the name. A scientist named Poynting, P-O-Y-N. This is called the Poynting vector. And so, just by itself, well, that's not that cool. But the fact is that when you take E and you cross it with H, you get a direction that is perpendicular to both E and H via the cross product. And so the resultant direction that you get points in the direction of propagation, right? Remember, the direction of propagation of the EM wave is both normal to E and H. So the reason why this is such a cool name is because it points in the direction of propagation. And that makes total sense. That's saying that the power is in the direction of travel. And why that makes sense. So imagine, like a tsunami wave, or, just a water wave. Of course, the power that wave is carrying is in the direction of the travel, the way the wave is traveling. It's certainly not like perpendicular to travel. So this makes total sense, and it's called the Poynting vector, named after the scientist Poynting. Very cool. Now, I'm going to erase our handy-dandy mathematics. There are little tricks. And you can summarize, what we've just kind of discovered as follows. So we have some EM, electromagnetic power, coming into some volume, right? Some system. So the power comes in, and we know from physics that power and energy always has to be accounted for. So we might get some out, we might not, depending on our system. But also now what we've just discussed is we have some ohmic losses, possibly, and this was the sigma E squared term. And we have energy that can be stored in the electric field. Electrical energy. Okay, stored electrical energy, 1/2. That was the 1/2 epsilon E squared term. And we have stored magnetic energy. Stored magnetic energy, that was the 1/2 mu H squared term. And then we have possibly power out. So actually we're accounting for all of the basic circuit analysis components. This is like a resistor, right? And what device stores energy in an electric field? That's the capacitance of the volume, right? And then what device stores energy in the magnetic field? That's the inductance of the volume. So what we're saying is EM power comes into maybe a circuit or something, and then some of that power is going to be lost versus heat, right, in the resistor. Some of it's going to be stored in the capacitor. Some of it's going to be stored in the inductance of the circuit, and some of it then just can get used to do something useful, like vibrate a speaker or something back and forth to make acoustical power, acoustical energy, something like that. All right. Now let's talk about average power, because average power is important to electrical engineering, because you don't usually talk about, take your computer or something. You don't usually talk about how much power it's consuming, like right now, or right now, you talk about battery life, like, hey, on average, I'm going to get like, 2 hours out of my Surface Pro or something, 2 hours out of my iPad. But so you talk about average power. So now let's kind of bring average power into the mix. So suppose our electric field is polarized linearly for right now. So we'll say that it points in the x direction. Like this. So we have this electromagnetic wave, we have this electric field. So the E field is pointing in the x direction, and it's traveling in the z direction. Then we know how E and H are related via the intrinsic impedance of the material. So remember the intrinsic impedance, eta, it has a magnitude, it's complex, so it has a magnitude and it has a phase. Alright, so how does the magnetic field behave then? Well, the amplitude, it gets scaled by the magnitude of eta, right? Think about complex arithmetic. And then the phase of the wave changes by the phase of the complex number, the intrinsic impedance. And we know that it must point in the y direction, which we've been over many times. Now the Poynting vector, there's my script P, that's a really bad script P. It is E cross H. Okay, so when you do the cross product here, you get E0 squared from the multiplication, you get over absolute value of eta, and then you get negative 2 alpha z as your exponent, because same base, add the exponents when you multiply, and you get cosine of omega t minus bz times cosine of omega t minus beta z minus that angle. And which direction is this in? Remember, the Poynting vector points in a direction perpendicular to both. Ax cross ay is going to give you az. Nice. Okay, now we can apply a trig identity. So cosine of a times cosine of b, which I had to look up. Full disclosure, so certainly don't memorize these things, is 1/2 cosine of a minus b plus 1/2 of cosine a plus b. But you see, I had to look that up, but I knew that the identity existed, right? So you need to be aware that these identities exist but at minimum, right? You know that the cosine of two things, you can separate those out. So now we get, let me try to make a better script P, our Poynting vector. Then if I apply that trig identity, is given by this thing, cosine of theta eta, that sounds nice, cosine twice okay. So I get this then when I apply that trig identity, right? And it's twice because omega t plus omega t when you add the two arguments together. Now, remember, we want to talk about time averaging power now. So what we're going to do is take, I'm going to get some space first, and then we're going to take the integral, or we're going to use some calculus to get the average value of this thing. So now I'm going to give script P and then subscript AVE for average. We're going to integrate this thing over the period of our wave. So here's our electric field, right? And it has a period of 2 pi over omega. And same with this thing. That thing has a period of 2 pi over omega. And the idea is that if you take the average value over one period, then that's the average value over all time because it repeats. So so from calculus, the average value over one period is 1 divided by the period, integral from 0 to the period of script p dt. Okay, and I've dropped the vector because I'm only looking at the magnitude now. All right, so when I do that, when I integrate these two terms, first notice that this term, which is oscillating, this thing is going to average to 0. The cosine or the integral of a cosine integrated over one full period gives you 0. So now I just have to integrate this thing. And when you integrate that thing, well, that thing doesn't even depend on time. So then I can just tack on the capital T and divide by t. And so that gives me very, very nice result. 2 there, eta, absolute value of eta, e to the negative 2 alpha z cosine of theta eta. Okay, and then as a vector, so if I guess if I want to put on the vector, this is in the z direction, right? It points, all the power is going in the direction of travel. All right, great. So we're almost there. So we've got our time average. Now let's relate this to the electric and magnetic field. So since ES, work with phasors, is E0, e to the negative alpha z, e to the negative j beta z in the x direction, right? The phasor for our field, and similarly, the magnetic field has a phasor E0 over the absolute value of eta, e to the negative alpha z, e to the negative j beta z, and then we have e to the negative j theta eta in the y direction. Okay. Now we're going to use some slick math here. I'm going to erase some of this. I want you to notice that ES cross the complex conjugate of HS, which I'm denoting with this asterisk, that gives me the following: negative 2 AZ e to the j alpha eta in the z direction, of course, the z direction. So the e to the minus j beta z go away, because when you take the complex conjugate of h, this becomes e to the plus j beta z, and then when you do the multiplication, they add to an exponent of 0. E to the 0 is 1. All right. Now let's just use Euler's formula. And so we can write this as cosine of theta eta plus, I'm running out of room here, j times this, and we will have the sine of theta eta. So remember here in my this was my average power that I wanted to relate to the electric part and the magnetic part, and so I see it kind of right there, right? It's almost there. It's off by a factor of 1/2. And so what I can say then is my average power is 1/2 the real part, because I'm ignoring this j here, I've only circled the real part, of ES cross the complex conjugate of HS, like that. Okay, and then just remember that E cross H has units of watts per square meter. So then the total time average power going through a surface then is given by this. So this again, this is not a script p, this is a regular p. So this was watts per square meter. Then if we integrate that over the surface area of some surface, then we have the total time averaged power. And again, the fact that electromagnetic waves carry power, this allows for the transmission and reception how electromagnetic waves propagate. We're going to look at how they reflect and they transmit when they get to different interfaces. So I will see you then.